All right, it's about noon central, our time, and today, as you all know, our seminar will be held virtually because we have a remote speaker here. It's Mr. Isaac McMahon from the University of Michigan, where he's a third-year graduate student. He was in Carnegie Mellon before that, and I think some of you may know that there is a connection to LSU. In specific, Isaac's dad is a graduate of LSU medical physics program. So hope I said that correctly, Isaac. Correct me if I'm wrong.
Health physics radiation, yeah.
Health physics radiation. Yeah, perfect. So without further ado, I'd like Isaac take the stage and then talk to us about a short guide to multi-messenger cosmology. Thank you.
Hello, everyone. I'm Isaac, like he said. I'm a third year at Michigan. A lot of my research deals with kind of this interface between observational astronomy, gravitational wave detection, as well as cosmology in the universe as a whole. So I just wanted to give an overview about how these things mesh together and what our research group is doing. So I work in the Soros Santos group at the University of Michigan. We're associated mainly with the Dark Energy Survey as well as DESI and a lot of different surveys. So to start off, I assume that at LSU, you guys have heard a lot about LIGO and operations. This talk was originally meant for a symposium at the University of Michigan where, I wanted to give more of a background about operations at LIGO and gravitational wave detection. But for this talk, I'm going to gloss over those a little bit and talk more about our research and what we're doing in multi-messenger physics and how the cosmology side is going. But just as an overview, the gravitational wave network is currently a network of 5 observatories all over the world that are observational currently, with a couple more on the far horizon. All of these work together to corroborate detections of gravitational waves. And the more detectors you have, the better your measurement. And here's a picture of the Livingston site, which is dear to me because I grew up in Baton Rouge. And this site was very important for my scientific development. But essentially, all of these sites are made up of interferometers with long tunnels that go off in different directions. A laser shoots down every tunnel and comes back, and this measures the strain or the warping of space due to gravitational waves. And so this light is reflected back and forth hundreds of times before it's detected, and this provides a measurement for binary black holes that are merging way out in the universe somewhere. Here's what that data actually looks like. So this is an example from GW170814. This event was significant because it was the first event to be detected in 3 separate detectors at the same time. So on the first row here, you can see the signal-to-noise ratio versus time. Here you clearly see a bump in the signal-to-noise at the same spot in time for all 3 detectors, which means that they were detected at the same time. The second row here is called a Q transform. This is essentially a frequency or a Fourier transform over time that shows you how much energy is in each frequency at every point in time. So you can see this characteristic upward curve in the signal. And this just tells you that over time, the 2 compact objects are spinning faster and faster around each other, so the frequency of the wave is increasing until it reaches a certain point where they collide and you can no longer see the signal. And the bottom row here shows the strain or the waveform of the gravitational wave as is detected in a detector, and it's overlaid over the noise here. So you can see what it actually looks like in the data. But this isn't all we get from a gravitational wave detection. Very important for us is the localization or the probability sky map of where these events are in the sky. So we get these banana-like shapes or blobs across the sky that tell you, okay, the event is 90% probable to be in this region, and some spots in this region are more probable than others. So we use this data to figure out, okay, where can we point our telescopes to try to find evidence of this gravitational wave event, of this binary black hole colliding or binary neutron stars colliding. This is what we really care about. So how do we get these predictions? How do we get parameters out of the data? We use a process called Bayesian inference. So these parameters of the gravitational waves are found using Bayes' law. You have your your posterior, which is equal to the likelihood times the prior over the evidence. This is a very common equation in statistics and likelihood estimation, things like that. And what we try to do is likelihood maximization, where you have a data vector, or you have your data waveform, and you're trying to match a model to it, h of k, according to your parameters, and you're trying to find a model which best fits the data over a lot of iterations. And your model is dependent on the parameters of your system, which is theta. And binary black hole systems can be fully described by 15 independent parameters, which I'll explain in a second. But this Bayesian inference in practice is implemented using a couple different algorithms like nested samplers or Markov chains. There's a couple that are important for analysis of gravitational waves, such as Bayes star for rapid localization. So LIGO uses Bayes star to pump out a probability sky map within the first couple of minutes after detection. And then there's other algorithms such as law inference or Bilby that provide a better estimation of all 15 parameters a couple hours to days after the detection. So there's a lot of different ways to implement this, and there's a lot of details here. But I want to talk about what these parameters actually are. So the binary black hole events are described by 15 base independent but correlated parameters. So at the basics, you have, each black hole has a mass. So that's 2 parameters. Each black hole has a angular momentum associated with it, which is a vector. So taken together, that's 6 extra parameters. There's inclination and polarization, which is associated with the total angular momentum of the system and how it's oriented. Then there's right ascension and declination, luminosity distance, which tells you where it is in the sky, the time and phase of the signal. And then you can add more parameters if you want to model extra physics. An example would be tidal deformation. So neutron stars are not perfectly compact. If you have a heavy, high mass object next to a neutron star, you might be able to deform the surface of the neutron star to have a bump on it. And this bump can actually affect the waveform of the gravitational wave. And so this can go into your model of how you want to fit the data. And if you want to add tidal deformation, you need to add more parameters, and your algorithm takes longer. But these 15 parameters are the basics. And this is what we generally deal with. Now, as a cosmologist and as an analyst, what I really care about is the so-called extrinsic parameters of the system. These are things such as the right ascension, declination, and luminosity distance, because this tells us more about the distribution in space as a whole, rather than the astrophysical distribution of like what kind of masses are involved, what kind of spins are involved, how does this affect the region around the event. I'm more concerned about what does this tell us about the universe as a whole. So a lot of the time in my research, I really ignore the masses, I ignore the spin vectors, because they are not very correlated with the right ascension, declination, luminosity distance, things like that. Here is kind of an example of output from a parameter inference algorithm for a gravitational wave event. here we have like a pyramid plot of a lot of covariances, and then you have posterior distributions for every parameter that tells you where it could be, and kind of an error region of where it could be. So that's just to give you an example of what this actually looks like. And you can tell that some parameters are definitely more correlated with each other than others. And we exploit that in a lot of ways. So far, the first 3 LIGO-Virgo observing runs have yielded 90 detections of gravitational wave events. This is what they all look like, kind of sorted by masses in this plot here. 2 of these events were binary neutron star systems. And one of those binary neutron star systems had an optical counterpart, which is very exciting, and which I'll bring up later. But the 4th observing run began on May 24th of this year, and it will continue for a year and a half. So this is an ongoing run, and we're currently doing science on it and trying to observe in the meantime. So that's the gravitational wave side of things. Now I want to talk about the cosmology side of things. So first of all, I want to show this horrible plot. It's really hard to find a good plot of the history of the Hubble constant, but the Hubble constant is a measure of the expansion rate of the universe. And in the last 100 years, there's been a lot of debate about the actual value of the Hubble constant, how the universe is actually expanding. And essentially, there's been a lot of fluctuation over time, but nowadays, this plot on the right shows you what the current landscape of Hubble constant measurements is. There's this disagreement between 2 methods of measuring the Hubble constant, and gravitational waves are here at the bottom as a newcomer, which hopefully will be able to say something actually relevant about the Hubble tension in the future. But right now, we're just getting onto the scene very, very nascently. So what is this tension? What is this disagreement? There's this disagreement between late universe measurements, which is essentially the universe around us, things that are in our local neighborhood, and early universe measurements, which have to do with the cosmic microwave background at the very early universe. So the late universe measurement is essentially the same type of calculation that Edwin Hubble did way back in the 1920s. We used a distance ladder. We have standard candles where we always know their luminosity. And you can plot the luminosity distance of things like supernovae and quasars and fit the luminosity distance curve to cosmological parameters, such as the Hubble constant, dark matter, dark energy, things like this. And so if you fit this curve perfectly, you can get a very good measurement for what the Hubble constant is. So that's very well defined. And now, recently, there's this early universe measurement from the cosmic microwave background. The way that this measurement works is essentially you have this this field of the cosmic microwave background in every direction. Here I have a picture of the Planck cosmic microwave background measurement. And this is essentially a map of density or temperature fluctuations all across the sky. And it's random. There's a lot of fluctuations here and there, but it's not completely uniformly random. There's some characteristic clumping here. There's cold regions, there's hot regions, and we can actually describe this clumping in terms of something called a power spectrum of Gaussian fluctuations. And this power spectrum and its coefficients depends on cosmological parameters, such as the Hubble constant, dark matter, dark energy, and all these things. So if you fit the curve for this power spectrum, you can actually recover cosmological parameters just from this cosmic microwave background measurement. So this was an independent measurement that gave a different measurement, or a different number for the Hubble constant. And currently, in our current scientific discussion, These two measurements, these two types of measurements, are in disagreement with each other to a significant degree. And so there's a lot of active debate about what is actually going on here. Is it some sort of systematic bias? Is it some sort of new physics that we don't know about? Is the Hubble constant actually a constant? Has it changed over time since the beginning of the universe? There's a lot to ask here. So what's great about gravitational waves and what we've done with gravitational waves is we can introduce a new measurement into this discussion. Now, gravitational waves are not electromagnetic waves. They're completely different. They're an independent probe, but we can still use them to measure the Hubble constant. And there's really two ways to do that. The first way is more direct and easier. This is the electromagnetic counterpart way. Essentially, how this happens is that we get a detection alert from LIGO, and we point our telescopes at the sky, and we're able to actually see the explosion that results usually from two neutron stars colliding. It's called a kilonova as opposed to a supernova. And if we observe this kilonova, we can identify exactly where it is because we can pinpoint the observation. We can identify the host galaxy. We can measure the recessional velocity of the host galaxy, and then use that with the luminosity distance from the gravitational wave to directly measure the Hubble constant. The Hubble constant is related directly to the luminosity distance and the redshift. There's a relation between the two there. So if you're able to detect directly using traditional telescopes the kilonova resulting from a gravitational wave event, then you're golden. You have a Hubble constant measurement. Now, in the case where you can't find the optical counterpart, there's still things that we can do. There's something called dark siren analysis. In this case, we haven't found the optical counterpart to the gravitational wave detection, but if this probability map overlaps with survey data that we've already gotten, that we've already taken, we already have some information about the galaxies in that region, right? So here is a plot on the right of a probability sky map for one of LIGO's gravitational wave events, plotted over galaxy distribution in the dark energy survey that was already taken and was just sitting there as a catalog that we have access to. We can now weight the redshifts of all the potential host galaxies in this probability region, and then statistically find an average redshift weighted by the probability for this gravitational wave event. So we say this galaxy is more likely, this galaxy is less likely. Let's find a weighted average redshift for all of these galaxies. And then you do the same thing. You compare it to the luminosity distance from the gravitational wave measurement, and then you measure H naught. This method is way less accurate, but essentially it's making something out of nothing. We have no measurement, we have no optical counterpart, but we can still say something about the Hubble constant if we have galaxy survey data in that region. If you don't have survey data in the region, then you're out of luck. You really can't do anything about it. So we've already done this analysis for several detections already. Here's what it looks like. On this plot, the blue bars are the canonical measurements of the Hubble constant. So you have the late universe, early universe measurements, and you can see that they're statistically different from each other. The gray curve is the electromagnetic counterpart measurement from GW 170817. We only have one of these, and it agrees with the other measurements, but the error bar is very large. And the red curve is the dark siren analysis for one event, and that one's even wider. You can't really say much with this measurement at all. So what can we do about this? How can we constrain these further? And there's really two ways to do this. One is waiting for more events. We're already doing that. We do a lot of weighting in this field. Anyone who does any kind of astronomy knows that weighting is a large part of the job. But while we're waiting, we can still do other things. So a lot of my research directly and what I've been working on is trying to improve parameter estimation for the data that we have already. Can we kind of squeeze more accuracy out of the data that we already have, and can we apply that to future data as well? So I'm going to go over both of these ways because our group actually does both of these, and we're actively involved in both observing new events and analysis of those events as well. So let's talk about observing first. Here's our pipeline inside the Dark Energy Survey. We have a working group here, and we have target of opportunity time on one of the telescopes in Cerro Tololo, Chile. So in Chile, there's this telescope on one of the mountaintops for the Dark Energy Survey, and we're able to take over this telescope if we need to, if there's a pressing event that we think will be a good observation target. So LIGO sends out an alert if they've detected something. We as a team wake up in the middle of the night if we have to. We all discuss about whether this event is a good event. Usually we'll think about whether or not our telescope is actually able to see that part of the sky, right? Because Chile, our telescope is 30 degrees south of the equator, so we're only able to really look at the southern sky. If our event is in the northern sky, there's not much we can do about that. Also, if the probability region sent out by LIGO is too large, we're not able to cover that entire region of the sky within the time frame, so we're not going to be able to find our event. So there's a lot of discussion about what constitutes a good event, and if we decide to actually pull the trigger on one of these events, then we send instructions to the telescope in Chile to say, point at this region of the sky, try to find all the high probability areas of this region, and let's try to find this optical counterpart. Then there's a lot of image processing to find transients with difference imaging. And then there's more processing, post-processing, and eventually we start to plot light curves of possible candidates. And then we evaluate them by eye. So we're saying, okay, is this one actually a transient? Have we seen it across all, like several days in a row? Does it match our predictions? Or generally, we try to differentiate between kilonovae and supernovae. Supernovae tend to have much longer decay times. So kilonovae evolve over the course of a week or two. Supernovae may evolve over the course of a month or two. And so we don't want transients that decay too slowly. We want transients to decay pretty fast. And eventually, by the end of this entire process, after several days of panic and sleepless nights, you have a pretty good idea of whether you've detected something or not. And so we've done this process several times. I think there's about 9 events here that we've done in the first 3 observing runs, this kind of observation target opportunity. Most of them have not panned out very well. So here's 3 examples on the right here of observation plans for several different events. On this map here, the white outline is the probability region given by LIGO. So this is LIGO telling us this gravitational wave event is probably in this region of the sky. And then all of these red and orange rings are the footprint of our camera and where it is observing over the course of several nights. And so you can see that over the course of several nights, we're able to cover a reasonable amount of the probability area, at least when we can, and try to say something about whether or not we can find the counterpart. Here you can see the footprint of the Dark Energy Survey. Kind of looks like a tank. Usually we want those events to fall within that footprint because we already have survey data in that region. It makes it a lot easier for us. But we can extend our range, our search range, to outside that footprint if we need to, because we can look at a lot of the southern sky if we need to. It's just that our search depth won't be as good in that region. So most of these events didn't really pan out. The reason for that being that most of these events are actually binary black hole events, which are not expected to really produce that much light, at least compared to binary neutron star events. And so a lot of these were just kind of testing the waters, seeing whether or not our pipeline actually works. And sometimes it's trying to actually find an optical counterpart. But there's a lot of trial and error here. There's a lot of trying to figure out how this is actually done. But we do have one golden event. This is GW 170817, and this is the observing plan for it. And we eventually found it at this spot in the probability distribution. And so this caused a big fanfare, a lot of fun, but we haven't really found anything similar in the last 6 years since then. And so hopefully we'll get another thing like this that allows us to constrain our measurements even further. So that's the observing side. Right now we're in the middle of 04 observing run. We've had some issues with the quality of data coming from LIGO. So hopefully we'll be able to have more detections within the next couple of months, but that remains to be seen. That's something actively being pursued right now. If we have a good event in the next day, hour, month, year, then we're going to be on the ground taking over the telescope and observing it. But in the meantime, now I want to talk about the analysis side and the other side to what I've been doing in multi-messenger cosmology. So I want to take you guys back to where I was talking about Bayesian inference and Bayes' law. There's something called the prior and the posterior distribution. And the prior is the constraint that you impose on your parameter. You're saying, these are the numbers that I'm allowing the algorithm to use to predict the right numbers for this parameter. Say you have, something about how masses are distributed in black holes. Like we can say it's a power law distribution of masses in black holes. Then you can input a power law as a prior in your algorithm to say, draw from this power law to figure out what the mass of this specific event could be. And that would be the posterior distribution, right? The eventual prediction for your probability distribution of your parameter based on your data, based on the models, and on the prior as well. So if you're able to justify strict constraints on your prior, your assumptions, then you can improve the posterior prediction of that parameter, but also other parameters that are correlated with that parameter. So just improving our assumptions on one parameter can actually have ripple effects in the other parameters because a lot of these parameters are correlated with each other. And so here's an example of that. In normal operation, our gravitational wave events are assumed to be equally likely in any direction. We make no assumption about where they come from. We say that any direction that you point could be a direction where this gravitational wave is originating. But we know that's not true, right? There's definitely an exact location of where this event really is. So for GW 170817, this was our optical counterpart detection event. But before the detection, there was still a probability sky map that gave us a prediction of where where it could be. And part of this estimation gave also a distance measurement. So it predicted that the luminosity distance measurement was about 40 megaparsecs plus 8 minus 14. But after the detection, after all the cosmological analysis and everything, they went back and ran those parameters. They re-estimated the parameters, but this time they used the exact location of the optical counterpart as a prior. So they said, we know exactly where our optical counterpart is, so we can use this as an assumption to maybe improve our other parameters. And what ended up happening was that the distance measurement improved, the errors on the distance measurement improved by a factor of 2. So the new measurement was 40 megaparsecs plus 3 minus 7. So just by constraining the right ascension and declination, the coordinates of this event, they were able to actually improve the distance measurement to the event. And this is important because, remember, we use distance to measure the Hubble constant. So if we can improve our distance measurement, that means the error on our measurement for the Hubble constant is also much better. So how can we use this fact? We already know where a lot of galaxies are, sometimes in certain regions of the sky out to a certain distance, but we have a lot of surveys that are pointing all over the sky and taking in a lot of data about the galaxies in our area. And for gravitational waves, we don't need to look out that far. We definitely don't need to go above z equals 1. We're really only dealing with our local neighborhood, or at least in the bigger picture of things, our local neighborhood. And we have a lot of survey data in that area. So what if we used our knowledge about galaxy distributions in the sky as a prior for our parameter inference? What if instead of not assuming anything about where our galaxies are coming from, or where our gravitational wave events are coming from, what if we used our galaxy catalogs to weight that prior? What if we said, let's assume that our gravitational wave events can only come from the host galaxies that we know about. And so this is essentially a middle ground constraint in between not assuming anything about the distance and assuming a perfect measurement of the distance. We can assume that theoretically, our gravitational wave events are supposed to happen in galaxies, not in intergalactic space. And we know where these galaxies are, so we can use this data to improve our measurement. So this is very preliminary research. I have some very early results from simulations that I've been doing, and it's very promising. What this plot is showing here is the same exact gravitational wave event, but in 3 different localization priors. So essentially, I'm measuring the luminosity distance using the same gravitational wave event, but in each case, the only thing I've changed is the assumptions I give the algorithm for right ascension and declination, the coordinates in the sky. For the blue curve, I assume nothing about where the event is. So that's the baseline. For the green curve, I give the algorithm the exact location of where the event is. For the orange, I have this middle ground constraint of the galaxy distribution, which is some information about where the event could be. And you can see that there's a clear progression in accuracy as you tighten those constraints. There are a couple problems with this plot. This is very early research, the things that have to do with tying down the uncertainty and things like that. But there's a very clear trend that we can affect our distance measurement strongly only by constraining our right ascension and declination. We can use the information that we have already to do this on previous data and on future data. So looking towards the future, O4, the Observing Run 4 for LIGO, is currently up and running. We've had some difficulties. We haven't had a good candidate for observation so far. But we're optimistic that we should be able to find some things in the near future. I think that this kind of work with measuring cosmological parameters with a lot of different probes is both scientifically and just cool in general. Like, I love talking about this stuff, and I think I'm very excited about this region that hasn't really been explored before, where the gravitational wave community and the survey community and the cosmology community haven't really talked with each other as a whole so far. But this field is kind of on the forefront of that, where this multi-messenger analysis is starting to combine all these disparate fields of observation to really do new things with science. And this is very new. We've only been doing this for less than a decade. This has only been possible for less than a decade. And so this field can only grow either by new detections or by improving analysis. The gravitational wave measurement of the Hubble constant is going to improve. Gravitational waves aren't really going anywhere in the near future. So we're going to get better at this. And it's only going to get more accurate as we go on. And so hopefully, eventually, we can say something in the Hubble tension, say something about what gravitational waves add to the conversation there. So that's all I have for today. Thank you very much, everyone. Are there any questions?
Thank you, Isaac. Do we have any questions for Isaac from the audience?
I have a question. Or can you hear me?
Yes.
So when you talked about the possibility that the Hubble constant might not be a constant and vary with cosmic time, I think that what the Planck and the microwave background studies actually fit is the present day value of the Hubble constant, so which is the same as the local measurements attempt to measure. And so the tension is between H naught of today. Isn't that correct? Although obviously it is to some extent model dependent.
I don't believe that's true. I believe the CMB measurement is the direct measurement of the fluctuations of density in the CMB field. And so these density fluctuations are dependent on things such as the dark matter density, the energy density, and the Hubble constant in the early universe. And so that Hubble constant will affect how these densities interact with each other in the early universe. And so what we're seeing in the cosmic microwave background is the freeze frame of the density fluctuations at redshift 1100, which is the reionization and where the universe becomes transparent to light, and this configuration gets frozen, and these photons get stretched out in time, and that is affected by redshift. But ideally, all of these photons are affected by the same redshift. So we can account for that. And what we're measuring is the density fluctuations themselves.
Any other questions for Isaac?
Thanks, Isaac. I'm Suniti. I had a question on the gravitational wave-based estimate. The plot you showed comparing the GW-based estimates with the other two.
Yes.
Cursorily, it seemed to me that the GW-based estimate overlaps with the other two within uncertainty.
Yes.
Unlike the other two themselves with each other. Could you also clarify a bit what the driving factors are primarily for the uncertainty of the GW-based estimates, and how you anticipate them to change over time as you get more and more data?
Yeah, so the primary, I think the largest driver in this uncertainty estimate is the gravitational wave measurement, the luminosity distance from the gravitational wave measurement, because It's not very accurate, especially when you get further away from Earth. You can get some very large fractional uncertainties, up to like 50% in your luminosity distance, which is actually a nightmare for trying to do analysis like this. This particular event was very good for us in that it was close by and that we're able to pinpoint it very well. But essentially what this graph represents is proof of concept. We know that we can measure something that's in general agreement with both of the canonical measurements. But we need a lot more similar events to stack on top of each other before we can actually achieve like similar precision. And I believe the number is in the dozens to dozens of events like it to actually get to that sort of precision.
Thanks.
Okay. Any more questions for Isaac, please? If there's no more questions, I'd like to thank Isaac again for his very interesting talk, and appreciate you all for joining us virtually today. We'll see you all in person again next week. Thank you.
Thank you very much.